Before we begin, take a gentle moment to like this video and subscribe to the channel. It truly helps more than you know. And if you find comfort in calm journeys through the universe, leave a comment telling me where in the world you're listening from. Now, dim the lights, settle into your favorite resting place, and let the vastness of space carry you somewhere peaceful. There are no adverts here, just a quiet voyage into the deep. Tonight, we drift toward one of the most mysterious and soothing wonders of the cosmos: black holes. Black holes are not holes in the usual sense. They are not tunnels you could simply step into, nor are they empty voids. Instead, they are regions of space where gravity has grown so strong that nothing, not even light, can escape once it crosses a certain boundary. Imagine a place where gravity gathers itself into a silent, invisible embrace, holding everything close. That boundary has a beautiful name. It is called the event horizon. The event horizon is like the shoreline of a cosmic ocean. Once something passes that shoreline, there is no returning. From the outside, however, the event horizon appears calm and perfectly round, like a dark pearl resting in the fabric of space. Black holes form when very massive stars reach the end of their lives. For millions of years, these stars shine brightly, balancing their own gravity with the outward pressure of nuclear fusion. But eventually, the fuel runs out. When that happens, gravity wins. The star collapses inward, compressing its core beyond imagination. In that final moment, space itself curves deeply, and a black hole is born. Some black holes are only a few times more massive than our Sun. These are called stellar mass black holes. They are scattered throughout galaxies, quiet remnants of once brilliant stars. Others are far larger. At the centers of most galaxies, including our own Milky Way, reside supermassive black holes. These giants can weigh millions or even billions of times the mass of the Sun. At the center of our galaxy lies a supermassive black hole known as Sagittarius A star. It sits about 26,000 light-years away from Earth. Though it sounds distant, in cosmic terms, it is relatively close. Sagittarius A star gently guides the motion of stars around it, like a silent conductor leading an orchestra of light. Despite their dramatic reputation, black holes are not cosmic vacuum cleaners wandering through space. They do not roam the universe, swallowing everything in their path. If our Sun were magically replaced by a black hole of the same mass, Earth would continue orbiting almost exactly as it does now. The only difference would be the absence of sunlight. The gravitational pull would remain the same at that distance. The intense gravity of a black hole comes from its incredible density. Density is a measure of how much mass is packed into a given space. When a massive star collapses, its mass is squeezed into a region far smaller than before. In some cases, the core becomes so compressed that it forms what physicists call a singularity. A singularity is thought to be a point of infinite density, where the known laws of physics can no longer fully describe what happens. Around many black holes, there is a glowing structure known as an accretion disk. This disk forms when gas, dust, and sometimes even entire stars spiral toward the black hole. As this material spins faster and faster, it heats up dramatically, glowing brightly in X-rays and other forms of radiation. Ironically, while black holes themselves emit no light, their surroundings can become some of the brightest regions in the universe. As matter spirals inward, it does not fall straight down. Instead, it forms a whirlpool-like pattern, similar to water circling a drain. Friction within this swirling disk can cause temperatures to rise to millions of degrees. The light produced by this heated material can travel across vast cosmic distances, allowing astronomers to detect black holes indirectly. Some black holes produce enormous jets of energy that shoot outward from their poles. These jets can extend for thousands of light years into space. They move at speeds close to the speed of light, carrying particles and radiation far beyond their host galaxy. The exact mechanism behind these jets is complex, involving magnetic fields twisted by the spinning black hole and its disk. Black holes can also spin. In fact, many of them rotate incredibly rapidly. When a black hole spins, it drags space-time itself around with it. This effect is called frame dragging. Imagine placing a heavy ball on a stretched rubber sheet and then spinning the ball. The sheet would twist around it. In a similar way, a rotating black hole twists the very fabric of space. Time behaves differently near a black hole. According to Einstein's theory of general relativity, gravity can slow down time. The stronger the gravity, the slower time passes relative to an outside observer. Near the event horizon of a black hole, this time dilation becomes extreme. To someone watching from far away, a clock near the event horizon would appear to tick more and more slowly. If you could safely observe someone falling toward a black hole, you would see them appear to slow down as they approach the event horizon. Their image would gradually fade and redden, never quite seeming to cross the boundary. From their own perspective, however, they would continue inward without noticing anything special at the exact moment of crossing. The stretching effect caused by intense gravity near a black hole has a strangely playful name. It is called spaghettification. As an object approaches very close, the difference in gravitational pull between its near side and far side can become enormous. This difference would stretch the object lengthwise and compress it widthwise, like a strand of spaghetti. Not all black holes are actively feeding. Many are quiet, almost invisible against the dark backdrop of space. Without an accretion disk or nearby material, they can be extremely difficult to detect. Astronomers often find them by observing the motion of nearby stars. If a star is orbiting an unseen object with tremendous mass, that hidden mass is often a black hole. In 2015, scientists made a groundbreaking discovery. They detected gravitational waves for the first time. These waves were ripples in space-time caused by two black holes merging far away in the universe. When massive objects accelerate, especially in violent events like collisions, they send out these ripples. By measuring them, we can hear cosmic events that would otherwise be invisible. Gravitational waves travel at the speed of light. When they pass through Earth, they stretch and squeeze space by incredibly tiny amounts, smaller than the width of a proton. Special detectors called LIGO and Virgo are designed to measure these minuscule distortions. Through them, we have opened a new window into the universe. In 2019, humanity saw the first direct image of a black hole. The Event Horizon Telescope, a network of radio telescopes spread across the globe, captured the shadow of a supermassive black hole in the galaxy Sunny 87. The image showed a glowing ring of light surrounding a dark center. That dark region was the black hole's shadow, cast against the luminous accretion disk. The sight of that image was both humbling and comforting. After decades of theory and indirect evidence, we finally glimpsed something once thought impossible to see. It was not a gaping void, but a graceful circle of light and darkness intertwined. Black holes challenge our understanding of reality. They sit at the intersection of gravity, quantum mechanics, and the geometry of space-time. Scientists continue to study them, hoping to unify the laws that govern the very large and the very small. In many ways, black holes are cosmic laboratories, pushing physics to its limits. And yet, despite their intensity, there is something deeply calming about them. They remind us that the universe is vast beyond measure, that there are forces at work far greater than our daily worries. In the grand scale of cosmic time, stars are born, they shine, they fade, and sometimes they collapse into these silent guardians of gravity. As you breathe slowly and steadily, imagine floating safely at a great distance from a black hole. You are far beyond its reach, simply observing. Around you, stars shimmer like distant candles. The black hole rests quietly, a dark sphere against a field of light. It does not roar, it does not chase, it simply exists, bending space in elegant curves. Let your thoughts drift like dust in an accretion disk, moving gently in circles. There is no rush here, no urgency, only the steady rhythm of cosmic motion. In the next part of our journey, we will continue to explore more soothing and fascinating truths about black holes, their origins, their strange properties, and the surprising ways they shape galaxies. For now, relax your shoulders, unclench your jaw, take another slow breath in and out. The universe is vast, and tonight it is peaceful. Let your breathing settle into a slow, steady rhythm. There is nowhere else you need to be. The universe is not in a hurry, and neither are you. We continue drifting gently through the darkness, guided only by distant starlight and quiet curiosity. Black holes may seem rare and exotic, but they are more common than you might imagine. In our Milky Way galaxy alone, scientists estimate there could be millions of stellar mass black holes. Most of them are invisible, wandering silently between the stars, detectable only through their gravitational influence. These smaller black holes are born from massive stars, typically those at least 8 times heavier than our Sun. When such a star exhausts its nuclear fuel, it can no longer resist its own gravity. The core collapses in a fraction of a second. The outer layers may explode outward in a brilliant supernova, briefly outshining entire galaxies. What remains behind, if the core is heavy enough, becomes a black hole. Supernovae are among the most energetic events in the universe. For a short time, a single exploding star can radiate more energy than our sun will emit over its entire lifetime. Yet, from that violent finale emerges something quiet and dark, a black hole, invisible but immensely powerful. There is another category of black holes called intermediate mass black holes. These are thought to range from hundreds to hundreds of thousands of times the mass of the Sun. For a long time, they were purely theoretical, like missing pieces in a cosmic puzzle. In recent years, evidence has begun to suggest that they do indeed exist, perhaps forming through repeated mergers of smaller black holes. And then there are the giants, supermassive black holes. Almost every large galaxy we observe appears to host one at its center. These cosmic titans can contain millions or even billions of solar masses, all concentrated into a region no larger than our solar system. Despite their size, they are still remarkably compact compared to the galaxies they inhabit. The relationship between galaxies and their central black holes is deeply connected. Observations show a surprising pattern. The mass of a galaxy's central black hole is closely related to the size and mass of the galaxy's central bulge of stars. It is as if the galaxy and its black hole grew together, influencing each other over billions of years. When a supermassive black hole actively feeds on surrounding matter, it can become what astronomers call an active galactic nucleus. The infalling material forms a bright accretion disk, and enormous amounts of energy are released. In some cases, the central region becomes so luminous that it outshines the rest of the galaxy combined. These extremely bright objects are known as quasars. Quasars are among the most distant objects ever observed. Their light has traveled for billions of years before reaching Earth. When we look at a quasar, we are seeing the universe as it was. When it was produced near a feeding black hole, is astonishing. As matter spirals inward, gravitational energy is converted into heat and radiation. This process can be more efficient at producing energy than nuclear fusion, the reaction that powers stars. In fact, pound for pound, accreting black holes can release more energy than stars do. Despite their power, black holes are governed by surprisingly simple rules. According to a principle often summarized as black holes have no hair, a black hole can be completely described by just three properties: its mass, its spin, and its electric charge. All other details about the matter that formed it are hidden behind the event horizon. This simplicity is both elegant and mysterious. No matter what falls in, gas, dust, planets, or even light, the black hole retains only those three measurable characteristics. The rest becomes inaccessible to the outside universe. The size of a black hole's event horizon depends on its mass. The radius of this boundary is known as the Schwarzschild radius. For an object with the mass of our Sun, that radius would be about 3 kilometers. For Earth, it would be less than a centimeter. This means that if Earth were compressed into a sphere the size of a marble, it would become a black hole. But such compression is far beyond anything that occurs naturally for planets. Only the cores of very massive stars can collapse in this way. Gravity must overcome all other forces, including the quantum forces that resist compression at the smallest scales. Inside the event horizon, our current understanding of physics reaches its limits. The equations of general relativity predict the existence of a singularity, a point of infinite density. However, many physicists believe that a complete theory of quantum gravity would replace this singularity with something more physically realistic. One fascinating idea suggests that black holes may slowly lose energy over time through a process known as Hawking radiation. Proposed by physicist Stephen Hawking in the 1970s, this theory combines quantum mechanics with gravity. According to the idea, tiny particle pairs constantly form and annihilate in empty space. Near the event horizon, one particle could fall in while the other escapes, causing the black hole to lose a small amount of mass. Hawking radiation is incredibly weak for large black holes. A supermassive black hole would take far longer than the current age of the universe to evaporate completely. But in principle, black holes are not entirely eternal. Given enough time, trillions upon trillions of years, they may slowly fade away. The concept of evaporation gives black holes a surprisingly gentle ending. Rather than remaining forever, they might eventually dissolve into faint radiation, returning their energy to the universe. Black holes also play a role in shaping galaxies. The powerful jets produced by active supermassive black holes can push gas away from the galactic center. This process can slow down or even halt star formation. In this way, black holes may regulate the growth of their host galaxies, acting as cosmic thermostats. When two galaxies collide, their central black holes can begin a slow gravitational dance. Over millions of years, they spiral closer together, eventually merging in a cataclysmic event. The collision releases enormous gravitational waves, rippling outward across space-time. These mergers are among the most energetic events in the cosmos. Yet, they unfold over vast distances and immense timescales, far removed from our daily experience. They are powerful, but also serene in their inevitability. There is something poetic about black holes merging. Two invisible titans circling one another, drawing closer with each orbit until they become one. The universe reshaping itself in silence. Astronomers continue to refine their methods for detecting black holes. Some are found through X-ray emissions from accretion disks. Others reveal themselves through gravitational lensing, where their gravity bends the light of background stars. In rare cases, a black hole may pass in front of a distant star, briefly magnifying its light. Gravitational lensing is a beautiful consequence of Einstein's theory. Massive objects curve space-time, and light follows those curves. A black hole, though invisible, can act like a lens made of gravity itself, distorting and amplifying the images of objects behind it. Even though black holes can be dangerous up close, at safe distances, they are simply part of the cosmic landscape. Our solar system orbits far from the Milky Way's central black hole, and there is no risk of being pulled in. Its influence extends only so far, just like the gravity of any other object. As you continue listening, imagine yourself floating peacefully near the edge of a distant galaxy. Far below you, a supermassive black hole glows faintly as matter circles in a slow spiral. Above you, countless stars shimmer in quiet harmony. The universe is not chaotic everywhere. Much of it unfolds in graceful patterns, orbits, rotations, cycles of birth and transformation. Black holes are part of that pattern, not destroyers of everything, but participants in a larger cosmic story. Allow that thought to settle gently in your mind. The cosmos is vast, structured, and deeply interconnected. Even its darkest regions have purpose and order. In the next part of our journey, we will explore even more calming and fascinating details about black holes, how they bend light, how they influence time, and how scientists continue to uncover their secrets. For now, let your breathing remain slow and even. Feel the quiet gravity of rest pulling you softly downward, like a peaceful orbit around sleep. The stars are still shining, and the universe is holding you gently in its vast, silent embrace. We continue drifting deeper into the 1000th year of the 21st century. We continue drifting deeper into the peaceful mystery of black holes, not rushing, not chasing answers, simply observing. Light behaves in extraordinary ways near a black hole. In everyday life, light travels in straight lines. It moves predictably, illuminating the world around us. But near a black hole, gravity bends space itself. And because light follows the curves of space-time, its path begins to arc and twist. This bending of light is called gravitational lensing. Imagine placing a clear glass marble on a sheet of paper covered in tiny dots. The dots behind the marble appear distorted and curved. In a similar way, a black hole distorts the image of stars behind it. The result can be rings, arcs, or multiple images of the same distant object. If you were far enough away to observe a black hole safely, you might see a glowing ring around it. This is sometimes called a photon ring. It forms because some light rays skim very close to the event horizon, looping around the black hole before escaping toward distant observers. These looping paths create a delicate halo of light, a shimmering circle against darkness. There is a special boundary around a black hole known as the photon sphere. At this distance, gravity is strong enough that light itself can orbit the black hole in unstable circular paths. Any small disturbance would send the light either spiraling inward or escaping outward. It is a fragile balance, a cosmic tightrope walked by photons. Time, too, begins to behave differently as one approaches a black hole. According to general relativity, the stronger the gravitational field, the slower time passes compared to regions with weaker gravity. This phenomenon is known as gravitational time dilation. Near a black hole, time slows dramatically. Imagine two clocks. One remains far from the black hole, safe in deep space. The other approaches the event horizon. To the distant observer, the clock near the black hole appears to tick more and more slowly. As it nears the event horizon, it seems almost frozen in place. Yet for someone traveling with that clock, time feels perfectly normal. Their heartbeat, their thoughts, their perception of seconds passing, all remain unchanged from their own perspective. It is only when compared to the outside universe that the difference becomes apparent. This stretching of time leads to fascinating possibilities in science fiction. But in reality, the extreme conditions near a black hole would make close exploration incredibly dangerous. Still, the mathematics describing these effects is precise and has been confirmed in weaker gravitational fields, even here near Earth. Black holes also stretch space itself. If you imagine space as a fabric, like a smooth sheet pulled tight, a black hole would create a deep well in that sheet. Objects moving nearby follow curved paths, not because they are being pulled in the traditional sense, but because the space they move through is curved. This curvature explains planetary orbits as well. Earth orbits the Sun not because it is being tugged by an invisible rope, but because the Sun bends space around it, and Earth follows that curved path. Near a black hole, the curvature becomes extreme. There is a region outside the event horizon called the ergosphere. This area exists around rotating black holes. In the ergosphere, space-time itself is dragged along by the black hole's spin. Nothing within this region can remain stationary relative to distant space. Everything is compelled to move in the direction of the black hole's rotation. The boundary of the ergosphere is not spherical like the event horizon. It bulges outward at the equator, forming a shape somewhat like a flattened sphere. Within this strange region, energy can, in theory, be extracted from the black hole's rotation through a process known as the Penrose process. The idea is subtle and elegant. If an object enters the ergosphere and splits into two pieces, one piece could fall into the black hole while the other escapes with more energy than the original object had. In this way, rotational energy is slowly drained from the black hole. While such processes are difficult to imagine practically, they reveal the deep and surprising physics hidden within these cosmic objects. Black holes are not only fascinating individually, they are also powerful tools for understanding the universe itself. By studying how stars orbit the supermassive black hole at the center of our galaxy, astronomers have been able to measure its mass with remarkable precision. Decades of observations have tracked individual stars moving in elliptical paths around an invisible point. Their motion leaves little doubt about the presence of an immense, compact mass. One particular star, known as S2, completes an orbit around Sagittarius A star roughly every 16 years. At its closest approach, it moves at thousands of kilometers per second. Observing its path has allowed scientists to test predictions of general relativity under strong gravitational conditions. Black holes also help us understand the early universe. In the distant past, when galaxies were young and chaotic, black holes grew rapidly. Some theories suggest that the first black holes may have formed from the collapse of enormous primordial gas clouds, even before the first generation of stars fully evolved. There is also speculation about primordial black holes, hypothetical objects that may have formed from density fluctuations shortly after the Big Bang. If they exist, they could range in size from microscopic to massive. Some scientists have even explored whether such primordial black holes could account for a portion of dark matter. Dark matter remains one of the great mysteries of modern astrophysics. It does not emit light, yet its gravitational effects are evident in the rotation of galaxies and the structure of the cosmos. While most evidence points toward unknown particles, The idea that tiny black holes could contribute is an intriguing possibility. The study of black holes brings together many branches of physics: gravity, quantum mechanics, thermodynamics, and cosmology. They sit at the crossroads of our understanding, inviting deeper questions. One of the most puzzling questions involves information. In quantum mechanics, information about a system is never truly destroyed. But if something falls into a black hole and disappears beyond the event horizon, what happens to the information describing it? This puzzle is known as the black hole information paradox. Physicists have debated this question for decades. Some propose that information is somehow encoded in subtle correlations within Hawking radiation. Others suggest that our understanding of space and time may need to change fundamentally to resolve the paradox. These questions may sound intense, but they are part of a calm and ongoing exploration. Science moves slowly, thoughtfully, like a careful walk through unfamiliar terrain. Black holes, despite their name, are not simply agents of destruction. They are engines of transformation. They shape galaxies, power quasars, generate gravitational waves, and challenge our deepest assumptions. And yet, from a safe distance, they are quiet. Imagine yourself now suspended far from any danger, simply observing a rotating black hole against a velvet backdrop of stars. Its accretion disk glows softly, a luminous spiral turning in graceful silence. Jets extend faintly from its poles, stretching into the darkness like beams of pale light. There is no sound in space, no roar, no crash, only motion without noise. Feel how small your worries are compared to this immense and ancient cosmos. The universe has been unfolding for nearly 14 billion years. Stars have lived and died, galaxies have merged, black holes have grown and collided, and through it all, there has been a quiet continuity, the steady unfolding of natural laws. Let your thoughts drift gently, like stardust caught in a slow orbit. There is comfort in the vastness, comfort in knowing that the universe operates on scales so grand that our momentary stresses dissolve into perspective. In the next part of our journey, we will explore even more soothing insights: how black holes interact with their surroundings, how scientists simulate them, and what the far future of a universe filled with black holes might look like. For now, simply breathe in and out. The cosmos is deep, the darkness is soft, and you are safe, floating peacefully among the stars. Let your breathing remain slow and steady. Feel the gentle rise and fall of your chest, like the quiet expansion and contraction of the universe itself. There is no rush here, only the calm unfolding of cosmic truths drifting toward you like distant starlight. Black holes do not exist in isolation. They are part of dynamic, ever-changing environments. Around many of them, entire systems evolve. Stars orbit, gas clouds swirl, and magnetic fields twist into intricate patterns. In regions where black holes actively gather material, the surrounding space can become astonishingly bright. The accretion disk, that luminous spiral of heated gas, does not simply glow, it pulses, flickers, and radiates energy across the electromagnetic spectrum. X-rays, visible light, radio waves, all can be produced as matter accelerates and compresses. The closer matter moves toward the event horizon, the faster it must travel to remain in orbit. This increasing speed generates friction within the disk, and friction creates heat. Temperatures can rise to millions of degrees, causing atoms to emit powerful radiation. From far across the universe, telescopes detect these emissions, revealing the presence of something otherwise invisible. Sometimes, the flow of material into a black hole is not smooth. It can occur in bursts. A star may wander too close, pulled by gravity into a fatal embrace. When this happens, the star can be torn apart in what astronomers call a tidal disruption event. As the star approaches, gravitational forces stretch it dramatically. The side closer to the black hole feels a much stronger pull than the far side. Eventually, the star is ripped into streams of glowing gas. Some of that gas escapes into space, while the rest spirals inward, temporarily lighting up the region with a brilliant flare. These events are rare and distant, but they allow scientists to observe black holes awakening briefly from dormancy. For a short time, the dark center of a galaxy can blaze with energy, then slowly fade back into quietude. Black holes also interact with magnetic fields in remarkable ways. In the swirling plasma of the accretion disk, magnetic fields become tangled and amplified. As the black hole spins, these fields can channel energy outward, launching jets from the poles. These jets are narrow beams of particles traveling at speeds close to that of light. The particles within the jets spiral along magnetic field lines, emitting radiation as they move. Some jets extend far beyond their host galaxy, stretching hundreds of thousands of light years into intergalactic space. They carry energy and matter outward, influencing regions far from their source. Yet even these immense jets unfold gradually across cosmic time. They are not sudden explosions, but steady streams shaped by rotation and magnetism. Scientists use powerful computer simulations to study black holes and their surroundings. Because we cannot travel near one directly, mathematics becomes our spacecraft. Equations describing gravity, fluid motion, and electromagnetism are combined into detailed models. These simulations allow researchers to visualize how matter behaves near the event horizon. They show turbulent disks glowing with heat, magnetic fields twisting like luminous threads, and jets forming along spinning axes. Through these digital explorations, we gain insight into processes that would otherwise remain hidden. Black holes can also merge quietly within dense star clusters. In regions where many stars are packed closely together, black holes may sink toward the center through gravitational interactions. Over time, they pair up, orbiting each other in tightening spirals. As they orbit, they lose energy through gravitational waves, faint ripples in space-time that carry energy away. The orbit shrinks, the dance quickens, and eventually the two black holes collide and become one. At the moment of merger, space-time itself vibrates intensely. The final black hole settles into a stable shape, emitting a final burst of gravitational waves known as the ring-down phase. It is as though the fabric of reality briefly rings like a struck bell before returning to stillness. These gravitational wave signals are delicate. By the time they reach Earth, they are incredibly faint, yet detectors have become sensitive enough to measure them. Each detection adds to a growing catalogue of black hole mergers, allowing scientists to map populations and understand their origins. There is something profoundly calming about this slow cosmic choreography. Black holes orbiting each other for millions or billions of years before merging. Galaxies drifting together over even longer timescales. Everything unfolds patiently. Black holes can also influence star formation in subtle ways. In galaxies where the central black hole is very active, the energy it releases can heat surrounding gas. Hot gas is less likely to collapse into new stars. In this way, a feeding black hole may slow down the birth of future generations of stars. It becomes part of a delicate balance, not merely consuming matter, but shaping the evolutionary path of its entire galaxy. And yet, galaxies continue to sparkle with countless stars. The presence of a black hole at the center does not spell doom. Instead, it adds structure and complexity to the grand design. In our own galaxy, Sagittarius A star is relatively quiet at present. It is not consuming large amounts of material. The stars near the galactic center orbit steadily, guided by gravity, but otherwise undisturbed. Our solar system, far out in one of the spiral arms, moves peacefully around the galactic core once every 230 million years. Right now, we are simply one tiny point in that immense orbit. And there is no sign of danger from the central black hole. It is too distant to affect us beyond its gravitational role in holding the galaxy together. Black holes may even play a role in cosmic recycling. When jets push gas outward, they can compress distant clouds. In some cases, this compression may trigger new star formation in neighboring regions. Thus, the energy from a black hole might indirectly contribute to the birth of new stars elsewhere. Destruction and creation intertwined within the same cosmic story. As you continue listening, imagine drifting near the outer edge of a glowing accretion disk. You are at a safe and impossible distance, untouched by gravity's extremes. The disk turns slowly beneath you, shimmering with soft light. The black hole itself remains unseen, its presence known only through the graceful motion around it. Stars in the background appear slightly distorted where their light passes close to the curved space. The entire scene feels suspended, timeless. The concept of curvature can be soothing when we allow it to be. Space bending gently, light following arcs instead of straight lines. Time flowing at different rates in different places. It reminds us that reality is richer and more flexible than it first appears. Even the darkest objects in the universe participate in this elegance. Black holes are not cosmic monsters lurking in shadows. They are natural outcomes of stellar evolution. They are governed by precise mathematical laws. They are woven into the structure of galaxies. And most importantly, they are far away. The universe contains vast expanses of empty space. The average distance between stars is enormous. Black holes, though numerous on a galactic scale, are separated by incomprehensible distances. The chances of encountering one by accident are extraordinarily small. Let that thought bring comfort. The cosmos is spacious, roomy, expansive. In the next part of our journey, we will explore more of the gentle mysteries surrounding black holes, their thermodynamics, their possible connections to wormholes, and the far distant future when the universe grows. grows dark and quiet. For now, allow your mind to float effortlessly. Your thoughts can orbit slowly, like stars around a distant center. Breathe in, breathe out. The universe continues its silent turning, and you are resting peacefully within it. Take a slow, unhurried breath in and gently release it. Feel the quiet weight of your body settling, as though gravity itself has softened just for you. We continue our calm journey, drifting deeper into the tranquil mysteries of black holes. There is a surprising connection between black holes and something as simple as temperature. At first glance, a black hole seems like the ultimate absorber, a place where energy goes in and never comes out. For a long time, scientists believed that black holes had no temperature at all. They were thought to be completely cold, eternal voids. But in the 1970s, a remarkable idea changed that perception. When quantum mechanics, the physics of the very small, is applied near the event horizon, something subtle appears. Tiny pairs of particles constantly form and vanish in empty space. Normally, they annihilate each other almost instantly. But near the event horizon, gravity can separate them. One particle may fall inward, while the other escapes into space. To a distant observer, it appears as though the black hole is emitting radiation. This faint glow is known as Hawking radiation. It is incredibly weak for large black holes, almost impossible to detect with current technology. But its existence suggests something profound. Black holes are not completely black. They have a temperature, and like all objects with temperature, they slowly radiate energy. Over unimaginably long timescales, they lose mass slowly, quietly, patiently. For a stellar mass black hole, this evaporation would take far longer than the current age of the universe. For supermassive black holes, the timescale stretches beyond comprehension, trillions upon trillions of years. Yet the principle remains. Even these giants are not forever. The idea that black holes can fade introduces a gentle symmetry to the cosmos. Stars are born, they shine, they collapse. Black holes form, they grow, and eventually, perhaps, they too dissolve into faint radiation. This brings us to the concept of black hole thermodynamics. In physics, thermodynamics describes how heat and energy move. It governs engines, refrigerators, and even the warmth of your own body. Remarkably, black holes obey similar rules. They possess something analogous to entropy, a measure of disorder or information content. In fact, a black hole's entropy is proportional to the surface area of its event horizon, not its volume. This is unusual. Most objects have entropy related to their internal contents, but black holes seem to encode information on their surface. This insight led to a profound idea called the holographic principle. The holographic principle suggests that all the information contained within a region of space could be described by information encoded on its boundary. Like a hologram, where a three-dimensional image emerges from a two-dimensional surface. Black holes, with their surface-based entropy, hint at this possibility. Perhaps the universe itself operates in a similar way. Deeper realities encoded on cosmic boundaries. There is something calming in this notion. That complexity can arise from simplicity. That vast interiors may be described by elegant surfaces. Another fascinating concept associated with black holes is the possibility of wormholes. In certain solutions to Einstein's equations, black holes could theoretically connect to other regions of space-time through tunnels known as Einstein-Rosen bridges. These hypothetical structures are often called wormholes. In theory, a wormhole could link distant parts of the universe, or even different universes entirely. However, such structures would likely be unstable, collapsing too quickly for anything to pass through safely. Exotic forms of matter with negative energy might be required to keep them open. At present, wormholes remain mathematical possibilities rather than confirmed realities. But they arise naturally from the equations describing gravity, and so they remain objects of quiet curiosity. Black holes also challenge our understanding of causality, the relationship between cause and effect. Inside the event horizon, all possible future paths lead inward. Just as time moves inevitably forward in our daily lives, space within the event horizon is oriented toward the singularity. It is not simply that escape is difficult, rather, every possible direction leads deeper in. This inversion of space and time near the event horizon is subtle and elegant. It shows how gravity reshapes the geometry of reality itself. Yet, from a safe distance, black holes behave predictably. Their gravitational pull decreases with distance, just like any other massive object. Planets, stars, and entire galaxies coexist with them peacefully. There is also a category known as rogue black holes. When galaxies merge, gravitational interactions can sometimes fling black holes away from their original centers. These wandering black holes travel through intergalactic space, invisible and alone. They carry with them the quiet memory of their former homes. Even so, space is vast beyond measure. The likelihood of encountering such a traveler is extraordinarily small. Scientists have also considered the smallest possible black holes. In theory, microscopic black holes could have formed in the early universe, or might even be produced in extremely high energy conditions. These tiny black holes would evaporate almost instantly through Hawking radiation, disappearing in flashes of energy. Although none have been observed, studying their theoretical properties helps physicists probe the relationship between gravity and quantum mechanics. Black holes also serve as natural laboratories for extreme physics. Near the event horizon, magnetic fields twist intensely. Particles accelerate to enormous energies. Conditions arise that cannot be replicated on Earth. By observing emissions from these regions, scientists gain insight into plasma physics, high-energy radiation, and fundamental forces. Even the mathematics describing black holes carries a certain elegance. The equations of general relativity, though complex, predict their existence with stunning precision. Solutions such as the Schwarzschild solution describe non-rotating black holes. The Kerr solution describes rotating ones. Each reveals different aspects of space-time curvature. These solutions are like carefully crafted poems written in the language of mathematics. And while the details can be intricate, the overall picture remains simple and calming. Gravity curves space. Mass tells space how to bend. Space tells matter how to move. As you rest, imagine the far distant future of the universe. Billions of years from now, stars will exhaust their fuel. Galaxies will grow dim. Black holes may become some of the last luminous engines feeding on leftover matter. Eventually, even they may fade through Hawking radiation, leaving a universe of faint particles drifting in darkness. This distant future is not something to fear. It is part of a grand cycle, playing out on scales so vast they feel almost abstract. The present moment, your breath, your awareness, exists within this enormous timeline. Black holes remind us that permanence is rare, change is constant. Even the most powerful gravitational wells are subject to the passage of time. And yet, within that impermanence, there is order, precise equations, predictable laws, rhythms of collapse and radiation, mergers and evaporation. Imagine now that you are observing a black hole from a tranquil vantage point, far enough away that its gravity feels like a gentle tug rather than a force. The accretion disk glows softly. The stars beyond shine steadily. Nothing rushes. Let your thoughts slow down, like matter spiraling gradually inward. Not falling, just circling peacefully. You are not near the event horizon. You are simply witnessing the quiet beauty of cosmic balance. In the next part of our journey, we will explore more of these calming insights. How black holes influence cosmic structure, what happens when entire clusters interact, and how scientists continue to refine our understanding through observation and theory. For now, allow yourself to drift. Feel the stillness. Feel the vastness. The universe is patient, and so are you. Settle a little deeper now. Let your body grow heavier against whatever supports you. Feel gravity as something gentle, something steady, something constant. The same force that shapes black holes is the force holding you softly in place right now. Black holes do not only influence individual stars, they shape entire clusters, galaxies, and even the large-scale structure of the universe. In dense star clusters, where thousands or even millions of stars are packed into a relatively small region, black holes can gather quietly at the center. Over time, heavier objects tend to drift inward through a process called mass segregation. Black holes, being among the heaviest stellar remnants, slowly sink toward the cluster's core. There, they may form binary pairs, two black holes orbiting each other in a slow gravitational dance. As these pairs orbit, they interact with nearby stars. Each close encounter steals a tiny bit of orbital energy from the black hole pair. tightening the remaining energy until the pair merges into one. This process can take millions or even billions of years. The universe is not rushed. On even larger scales, galaxies themselves interact. When two galaxies drift toward each other, their stars rarely collide directly. There is simply too much empty space between them. Instead, their gravitational fields weave together, distorting shapes and creating long tidal tails of stars and gas. At the centers of those merging galaxies, the supermassive black holes begin their own slow approach. For a time, two supermassive black holes may orbit one another within the newly forming galaxy. These dual cores can exist for millions of years, hidden behind clouds of gas and dust. Eventually, they too spiral inward and merge, releasing an enormous burst of gravitational waves. The final merged black hole may receive a slight kick from asymmetrical gravitational wave emission, sending it drifting slightly off-center before settling back into equilibrium. Even such colossal events unfold with quiet inevitability. Black holes also influence the distribution of matter between galaxies. In clusters of galaxies, immense collections containing hundreds or thousands of galaxies, supermassive black holes can inject energy into the surrounding gas. The jets produced by active galactic nuclei can heat intergalactic gas, preventing it from cooling too quickly. This heating process slows the rate at which new stars form within cluster galaxies. In this way, black holes help regulate the thermal balance of environments spanning millions of light years. It is remarkable that objects so compact can influence regions so vast. Scientists study these interactions using observatories across the electromagnetic spectrum. Radio telescopes map enormous jets stretching through space. X-ray telescopes detect hot gas heated by black hole activity. Infrared instruments peer through dust to observe hidden galactic centers. Each wavelength reveals a different layer of the story. Black holes also serve as precise cosmic clocks. When matter orbits close to a black hole, it can emit periodic bursts of radiation. These signals allow astronomers to measure orbital periods and test predictions of relativity. Slight shifts in frequency reveal how space-time is curved and how time slows near massive objects. The closer matter orbits to the event horizon, the stronger these relativistic effects become. Even light escaping from near a black hole loses energy, shifting toward longer wavelengths in a process known as gravitational redshift. It is as though gravity gently stretches the light itself as it climbs away. These subtle shifts confirm Einstein's predictions with extraordinary accuracy. There is also a surprising calmness in the mathematics describing rotating black holes. The Kerr solution, discovered in the 1960s, describes how space-time behaves around a spinning black hole. It reveals the existence of the ergosphere, where energy extraction is theoretically possible. It shows how frame dragging twists nearby space. It predicts stable and unstable orbits for matter and light. Despite the extreme conditions, the equations remain smooth and continuous. No sudden edges, no chaotic breaks, just curvature increasing steadily toward the event horizon. Black holes also help scientists explore the limits of measurement. At extremely small scales, quantum effects dominate. At large scales, gravity rules. Black holes sit precisely at the intersection of these regimes. understanding them fully may require a unified theory of quantum gravity, a framework that blends the very small with the very massive. Several approaches are being explored. String theory suggests that fundamental particles are tiny vibrating strings. Loop quantum gravity proposes that space-time itself may be quantized, woven from discrete units. Black holes provide testing grounds for these ideas. They are like cosmic puzzles, quietly challenging physicists to think more deeply. Meanwhile, in the observable universe, black holes continue their slow, predictable behavior. They orbit, they merge, they accrete matter, they radiate faintly, they influence their surroundings through gravity and energy output. And they do so without haste. Consider the timescales involved. The Milky Way will likely merge with the Andromeda Galaxy in about 4 billion years. Their central black holes will eventually meet. The stars of both galaxies will rearrange into a new structure. Yet for countless generations of life, should life persist, the night sky will simply evolve gradually. Constellations will shift, new patterns will emerge. Black holes do not bring sudden endings to galaxies. They are participants in long, graceful transformations. There are even black holes that exist in binary systems with ordinary stars. In these systems, the black hole and a companion star orbit a shared center of mass. If the star expands during its evolution, material can spill toward the black hole. This creates a bright accretion disk and strong X-ray emissions. Astronomers detect many stellar mass black holes this way by observing the energetic signals from their feeding phases. When the flow of material slows, the system dims again, returning to quiet orbit. Black holes are often portrayed dramatically in fiction, swirling maelstroms of destruction. But in reality, most of them spend long stretches in near silence. Space itself is mostly empty. Distances are vast beyond easy comprehension. The average separation between stars in our region of the galaxy is measured in trillions of kilometers. This spaciousness is comforting, even though there may be millions of black holes in the Milky Way. They are scattered across enormous distances. The chance of our solar system encountering one is exceedingly small. You are safe within a stable orbit around an ordinary star. Let that thought settle. Imagine now drifting above a cluster of galaxies. Below you, thousands of galaxies glow like soft lanterns suspended in darkness. At their centers, supermassive black holes anchor the swirling stars. From this vantage point, the universe feels orderly, structured, vast, yet coherent. Gravity weaves everything together, from planets to stars, from stars to galaxies, from galaxies to clusters, and black holes are simply dense knots in that grand tapestry. They do not disrupt the overall harmony. They are part of it. As you continue to relax, allow your mind to widen like the expanding universe itself. Thoughts can drift slowly outward, becoming lighter and less defined. In the next part of our journey, we will explore more serene ideas, the role of black holes in cosmic evolution, the ultimate fate of matter, and the quiet possibilities of what lies beyond the event horizon in theory. For now, breathe slowly, in and out. The cosmos stretches endlessly, and you are floating peacefully within its calm, gravitational embrace. Take a long, gentle breath in and let it drift out slowly. Imagine your thoughts becoming softer now, like distant stars fading into a velvet sky. We continue our calm exploration, moving deeper into the quiet philosophy of black holes and the long future of the cosmos. Black holes are not only objects in space, they are milestones in cosmic evolution. When the universe was young, it was simpler. Hydrogen and helium filled vast expanses. Gravity slowly gathered that gas into the first stars. Those stars lived fast and bright, forging heavier elements in their cores. Some of them ended their lives in collapse, leaving behind the earliest black holes. Over billions of years, these early black holes may have grown by merging with others and feeding on surrounding gas. In doing so, they became the supermassive anchors at the centers of galaxies. So in a way, black holes are part of the story of structure. Without gravity gathering matter together, there would be no stars. Without stars, there would be no heavy elements. Without those elements, there would be no planets, no oceans, no life as we know it. Black holes emerge from the same process that allows existence to unfold. There is something unexpectedly comforting in that connection. As galaxies matured, star formation gradually slowed. Gas was used up or heated by active galactic nuclei. The bright era of frequent quasar activity faded. Many supermassive black holes entered quieter phases, like Sagittarius A star in our own Milky Way. The universe itself continues to expand, and that expansion is accelerating. Distant galaxies are moving away from us faster and faster, driven by what we call dark energy. Over immense timescales, galaxies beyond our local group will drift beyond the observable horizon. Their light will stretch and fade. In trillions of years, the night sky from within our galaxy may appear darker, emptier. Only nearby stars and the merged remnant of the Milky Way and Andromeda will remain visible. Black holes will still be there. Stars will continue to form for a long time, but eventually, even star formation will cease. The raw materials will be exhausted. Existing stars will burn out one by one. White dwarfs will cool. Neutron stars will fade. Black holes will become some of the dominant objects remaining. Some stars may slowly spiral into central black holes over inconceivably long periods. Others may be ejected from galaxies through gravitational interactions. Gradually, the universe will become a quieter place. This era is sometimes called the degenerate era, a time when stellar remnants dominate. Even further into the future lies what some call the black hole era. During this time, most ordinary matter will have either decayed or been captured by black holes. Galaxies will be dark, except for the faint glow of matter occasionally falling into these gravitational wells. But even then, change continues. Through Hawking radiation, black holes will very slowly evaporate. Small ones first, then larger ones. The largest supermassive black holes may persist for unimaginable durations, far longer than stars ever did. But even they are not immune to time. Eventually, they too will radiate away their mass. The final stages of a black hole's evaporation may end in a brief burst of energy. After trillions upon trillions of years, the once mighty gravitational anchor dissolves into elementary particles. What remains is a thin, cooling sea of radiation and sparse particles drifting in expanding space. This distant vision is not bleak. It is serene in its inevitability. The universe evolves through stages like seasons on a scale beyond imagination. Birth, growth, transformation, quiet fading. Black holes are simply one chapter in that immense narrative. Now let us return to the present moment. Right now, the universe is vibrant. Stars are shining. Galaxies are colliding gently across vast distances. Black holes are merging and sending out ripples in space-time that we can measure. We are living in a particularly luminous era. Black holes also invite philosophical reflection. They challenge our intuitive understanding of reality. They blur the distinction between space and time. They raise questions about information, entropy, and the fundamental nature of existence. And yet, they do so quietly. They do not announce themselves with noise. They do not disrupt nearby regions without cause. Their influence follows precise mathematical relationships. Even the event horizon, that boundary of no return, is not a physical surface you could touch. It is a geometric threshold, a point in space-time where paths inward become inevitable. From a distance, it appears perfectly calm. If you imagine hovering safely near a black hole, far beyond danger, you would see stars wheeling overhead in distorted arcs. The accretion disk would glow like a luminous halo. The black center would appear as a perfectly dark circle framed by bending light. There would be no sound, no roar, just the silent curvature of space itself. Some theoretical ideas suggest that what we perceive as a singularity may not be the final truth. Quantum gravity might replace it with something finite and structured. Perhaps space-time becomes granular at the smallest scales. Perhaps new physics emerges within the deepest regions. We do not yet know, and there is peace in that uncertainty. Science does not demand that every mystery be solved immediately. It invites patience, careful observation, thoughtful revision of ideas as evidence grows. Black holes remain among the clearest reminders that the universe is larger than our current understanding. But they are also reminders that understanding grows steadily. Just over a century ago, black holes were purely mathematical curiosities. Today, we have imaged their shadows. We have measured their mergers through gravitational waves. We track stars orbiting invisible masses with exquisite precision. Knowledge expands gently, like ripples spreading across a still pond. As you rest now, imagine yourself floating far above the plane of a spiral galaxy. Below you, billions of stars form delicate arms curving around a luminous core. At the center, a supermassive black hole sits quietly, anchoring the motion. The entire galaxy turns slowly, completing one rotation over hundreds of millions of years. There is no urgency in that rotation, no hurry, just motion sustained by gravity and time. Let your own thoughts move like that. Slow, circular, effortless. Black holes are not endings. They are transitions. They are part of the universe's way of reshaping matter and energy. And even in the far future, when they themselves fade, the laws guiding them will still hold true. In the next part of our journey, we will explore even more calming dimensions of these remarkable objects, including the strange idea of information at the horizon, the geometry of space inside theoretical models, and how black holes help unify our picture of reality. For now, breathe deeply. Feel the steady pull of gravity beneath you. The universe is vast, the timeline is long, and in this moment, everything is still. Take another slow breath in, hold it gently for a moment, and release it. Let your thoughts soften even more now. We are drifting into some of the deepest and most subtle ideas surrounding black holes, ideas that stretch the imagination yet unfold with quiet elegance. There is a question that has puzzled physicists for decades. What happens to information when something falls into a black hole? In everyday life, information is never truly destroyed. If you burn a book, the pages turn to ash and smoke, but in principle, every particle still carries traces of the original arrangement. The information is scrambled, difficult to recover, but not erased. Quantum mechanics is built on this principle. The laws governing particles preserve information, but black holes seem to challenge this. If a star collapses into a black hole and later the black hole evaporates through Hawking radiation, what happens to the information describing the star? Is it lost forever behind the event horizon? Or is it somehow encoded in the radiation that escapes? This puzzle is known as the black hole information paradox. For many years, physicists debated fiercely. Some argued that information truly disappears, requiring a modification of quantum theory. Others insisted that quantum mechanics must remain intact, and therefore, the information must escape in some subtle way. Gradually, a new consensus began to form. Many researchers now believe that information is not destroyed. Instead, it may be stored on the surface of the event horizon itself, encoded in incredibly subtle quantum correlations. Hawking radiation, once thought to be purely random, might carry faint imprints of what fell in. This idea connects beautifully with the concept we mentioned earlier, that a black hole's entropy is proportional to the area of its event horizon. It suggests that the horizon is not just a boundary, but a kind of dynamic surface where information is woven into the fabric of space-time. Some physicists describe the event horizon as a holographic screen. Imagine that everything happening inside the black hole could be described by information on its surface, much like a hologram encodes a three-dimensional image on a two-dimensional sheet. This idea has grown into a broader framework known as holographic duality. In certain theoretical models, a gravitational system in a volume of space can be equivalent to a quantum system defined on its boundary. Two very different descriptions, mathematically equivalent. Two perspectives on the same underlying reality. Black holes have become central to exploring this duality. They are no longer seen merely as collapsed stars, but as keys to understanding how gravity and quantum mechanics might fit together. There is something deeply calming in this symmetry, that what seems lost may simply be hidden in another form, that boundaries may hold more meaning than we expect, that surfaces can encode depths. Some researchers have even proposed that space-time itself may emerge from quantum entanglement, the subtle connections between particles. In this view, geometry is not fundamental, but arises from relationships between quantum states. Black holes, with their extreme gravity and quantum behavior, become testing grounds for this profound idea. The more we study them, the more they appear not as cosmic monsters, but as bridges between theories. There is also a concept known as black hole complementarity. This idea suggests that different observers may have different, yet equally valid descriptions of reality near a black hole. To a distant observer, information never truly crosses the event horizon. It becomes smeared and encoded on the surface, but to an infalling observer, nothing unusual happens at the horizon. They pass through smoothly. Both perspectives can be correct within their own frames of reference. This challenges our intuitive sense that there must be a single, absolute description of events. Instead, reality may depend subtly on the observer's path through space-time. It is not chaos. It is consistency across perspectives. Another intriguing proposal is the firewall hypothesis. Some theorists suggested that to preserve quantum information, the event horizon might not be smooth after all. Instead, it could be surrounded by high-energy radiation, a kind of firewall. However, this idea remains controversial, and many physicists continue to search for alternative resolutions that preserve both smooth horizons and information conservation. The debate itself is calm and methodical. Equations are written, assumptions are tested, conferences are held, papers are revised. Science unfolds like the slow orbit of binary stars, steady, deliberate, guided by evidence. Black holes also inspire questions about the nature of singularities. General relativity predicts that at the very center, density becomes infinite and space-time curvature diverges. But infinities in physics often signal incomplete understanding. Many physicists suspect that a full theory of quantum gravity would smooth out the singularity, replacing it with a finite, perhaps highly curved but non-infinite structure. Some models suggest a bounce, where collapsing matter transitions into expansion. Others imagine that singularities connect to new regions of space-time. These ideas remain speculative, yet they illustrate something beautiful. Black holes push us toward deeper comprehension. Even the geometry inside a black hole, according to certain solutions, may be far stranger than simple collapse. In rotating black hole models, space-time includes inner horizons and complex causal structures. The mathematics describes pathways that twist and fold in ways difficult to visualize. And yet, from the outside, the black hole remains simple, a sphere defined by mass and spin. Quiet, dark, predictable. This duality between internal complexity and external simplicity is soothing. It reminds us that much of reality operates beneath surfaces we barely perceive. As you continue resting, imagine standing at a safe cosmic distance, observing the event horizon of a distant black hole. The boundary glows faintly with quantum fluctuations, tiny flickers of particle pairs forming and separating. The surface is not rigid, but alive with subtle motion. Beyond it lies a region inaccessible to you, yet governed by the same fundamental laws. There is no need to know every detail. It is enough to recognize that the universe is coherent, even where it is mysterious. Black holes teach patience. They remind us that understanding deepens over time, that apparent contradictions can lead to richer frameworks, that boundaries may hold secrets not yet fully revealed. In many ways, they are invitations to question assumptions, to refine theories, to remain open to revision. And through it all, they remain distant, far safely removed from our daily lives. Right now, Earth orbits the Sun peacefully. The Sun orbits the center of the Milky Way. The central black hole anchors that motion gently from far away. Its gravity contributes to the stability of our galactic home. Let that stability comfort you. The same force that bends light and slows time on cosmic scales is the force keeping your feet on the ground. Gravity is not something foreign or threatening. It is familiar. Black holes simply represent gravity in its most concentrated form. In the next part of our journey, we will explore how black holes are observed in even greater detail, how future telescopes may reveal more of their shadows, and how they continue to guide our understanding of cosmic reality. For now, allow your thoughts to grow lighter. Let them hover at the edge of the horizon, not crossing, not falling, just resting in quiet curiosity. Breathe in slowly and out. The universe holds its mysteries gently, and you are floating peacefully within its vast, unfolding design. Take a slow, steady breath in and release it softly. Feel how effortless it is now to drift along with these ideas. We are nearing the outer edges of our journey, yet the universe itself continues endlessly. Tonight, we explore how black holes are observed with ever greater clarity, and how future discoveries may deepen this calm understanding. For most of human history, black holes were invisible not only to the eye, but to imagination. They existed only as solutions to equations, quiet predictions written in mathematical language. Today, we observe their presence with remarkable precision. One of the most extraordinary achievements in modern astronomy was the creation of the Event Horizon Telescope. This was not a single telescope, but a network of radio observatories spread across the Earth. By linking them together using a technique called very long baseline interferometry, scientists effectively created a telescope the size of our planet. The larger the telescope, the finer the detail it can resolve. In 2019, this global instrument captured the first image of a black hole's shadow in the galaxy M87. The image showed a glowing ring of hot plasma encircling a dark center. That dark region was not the black hole itself, but its shadow, the silhouette created by extreme gravitational bending of light. It was a quiet triumph. No explosion, no dramatic spectacle, just a blurred orange ring against darkness. Yet within that image lay confirmation of decades of theoretical work. In 2022, the Event Horizon Telescope team revealed an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy. Though smaller than the one in M87, it appeared similar, a glowing ring shaped by curved space-time. The fact that black holes across different galaxies share these visual characteristics reinforces the elegance of general relativity. Future improvements to this telescope network may sharpen these images even further. Additional observatories, perhaps even space-based radio telescopes orbiting Earth, could increase resolution dramatically. One day, we may watch changes in the accretion disk in near real time. Gravitational wave observatories are also evolving. The detectors currently operating on Earth have already observed dozens of black hole mergers. Each signal is brief, a rising chirp lasting less than a second. But within that chirp lies information about mass, spin, and distance. Future detectors, both ground-based and space-based, will expand this capability. A planned mission known as LISA, the Laser Interferometer Space Antenna, will consist of 3 spacecraft orbiting the Sun in a triangular formation millions of kilometers apart. It will be sensitive to lower frequency gravitational waves, such as those produced by merging supermassive black holes. This will allow us to observe entirely new classes of cosmic events. Instead of just seeing the final collision, we may track the gradual in-spiral of massive black hole pairs over months or even years. Listening to the universe in gravitational waves is a gentle experience. These ripples are not violent where we are. They pass through Earth without harm, stretching space by tiny fractions of a proton's width. Yet they carry stories from billions of light years away. Astronomers are also studying black holes through stellar motion with increasing precision. Advanced instruments measure the positions of stars near Sagittarius A star with astonishing accuracy. By mapping their orbits, scientists test relativity under strong gravity. So far, Einstein's theory continues to hold. There is comfort in this consistency. The same equations that describe the bending of light near a black hole also describe the orbit of Mercury around the Sun. The universe operates under unified principles, from the familiar to the extreme. New telescopes, such as the James Webb Space Telescope, peer into dusty galactic centers in infrared light. They reveal regions once hidden from view. By observing early galaxies, astronomers study how supermassive black holes formed so quickly in the young universe. Some black holes appear to have reached enormous sizes surprisingly early, challenging existing formation models. This pushes researchers to refine their understanding of cosmic growth. And yet, even as models evolve, the underlying rhythm remains. Gravity gathers matter, matter collapses, energy radiates, structure forms. Black holes also help calibrate cosmic distances. In certain cases, the motion of gas around a supermassive black hole can be measured precisely enough to determine the galaxy's distance from us. This contributes to mapping the expansion of the universe itself. So these dark objects, which emit no light, help illuminate the scale of reality. There is a poetic symmetry in that. Black holes may also play a role in the search for fundamental particles. If microscopic black holes were ever detected, perhaps indirectly through high-energy cosmic rays, they could reveal extra dimensions or new physics beyond the standard model. While no such detections have occurred, the possibility remains a topic of quiet investigation. Even theoretical simulations are becoming more sophisticated. Supercomputers now model black hole mergers in extraordinary detail, predicting gravitational waveforms before they are observed. These simulations match real detections with stunning accuracy. It is as though we are learning the language of black holes, not through sight alone, but through vibration and motion. As you rest now, imagine humanity observing the universe, not with fear, but with patience. Telescopes pointed gently toward distant galaxies, detectors listening for faint ripples in space-time. mathematicians refining equations in quiet rooms, the pursuit of understanding unfolds steadily, generation by generation. Black holes, once thought to be purely destructive, have become central to this exploration. They anchor galaxies. They generate gravitational waves. They test the limits of theory, and they do so from unimaginable distances. Right now, countless black holes exist across the cosmos. Some are merging, some are feeding, some are silent. Most will never affect our small corner of space in any noticeable way. We orbit peacefully within a stable solar system. The sun will shine for billions more years. Sagittarius A star remains far away, influencing us only as part of the Milky Way's graceful rotation. Let that distance feel reassuring. The universe is vast enough to hold extreme phenomena without bringing them close to home. Imagine floating now above the Event Horizon Telescope Array. The Earth turns slowly beneath you. Radio dishes across continents synchronize with atomic precision. Signals converge, data streams combine, and from that coordination, a faint ring of light emerges. The shadow of a black hole billions of times more massive than the sun. Human curiosity reaching across cosmic emptiness. In the next and final part of our journey, we will gently reflect on the larger meaning of black holes in our understanding of existence and close with a peaceful return to the present moment. For now, breathe deeply. The instruments are listening, the galaxies are turning, and you are resting safely within the quiet order of the cosmos. We have traveled far tonight. Before we gently return, take one slow, deep breath in and release it softly. Feel how calm your body has become. The universe is still vast, still unfolding, but you are here, steady and safe. Black holes, in all their mystery, are not symbols of chaos. They are expressions of gravity, the same force that keeps the moon in orbit around Earth, the same force that anchors you gently to your bed or chair right now. They are not interruptions in the laws of physics. They are confirmations of them. Over the course of this journey, we have drifted through their birth in collapsing stars, their growth at the centers of galaxies, their mergers that ripple space-time, their slow evaporation across unimaginable ages. We have explored how they bend light, slow time, encode information, and shape cosmic structure. And through it all, one truth remains steady. Black holes are part of the universe's quiet order. They follow precise equations. They emerge naturally from stellar evolution. They interact through gravity with predictable grace. Even their most extreme behaviors unfold over vast timescales. Nothing about them is rushed. Nothing about them is personal. They simply are. There is something deeply comforting in that simplicity. When a massive star reaches the end of its life, gravity gently gathers its core inward. The collapse is dramatic in energy, yet inevitable in physics. From that transformation, a black hole may form, compact, silent, defined by only a few properties: mass, spin, charge. Everything else hidden beyond the horizon. But hidden does not mean chaotic. It means beyond our current view. And throughout history, humanity has shown that what lies beyond today's horizon often becomes tomorrow's understanding. Black holes once existed only as mathematical curiosities, then as indirect hints in the motion of stars, then as X-ray sources in binary systems, then as gravitational wave signals, then as glowing rings captured by a planet-sized telescope. Each step forward has been calm and deliberate. Discovery rarely arrives as a sudden storm. It comes as careful listening, careful measuring, careful thinking. Even the most dramatic black hole mergers, when translated into gravitational waves, reach us as faint chirps, tiny distortions in space itself, gentle ripples crossing billions of light years. They pass through Earth unnoticed by our senses, yet instruments detect them, and knowledge grows. Black holes also remind us of perspective. The Milky Way contains hundreds of billions of stars. At its center lies a supermassive black hole 4 million times the mass of the Sun. And yet we orbit peacefully, 26,000 light years away, unaffected in our daily lives. Space is spacious, distances are vast, even extreme phenomena are softened by scale. The universe is not crowded, it is expansive. Imagine now that you are floating far above it all, above galaxies, above clusters, above the cosmic web itself. You see luminous filaments of matter stretching across darkness. At the nodes of these filaments, galaxies gather. At their centers, black holes anchor their motion. From this vantage point, nothing feels threatening, only structured, elegant, balanced. Gravity weaves the tapestry. Time carries it forward. Energy transforms, but is never lost. Even in the far future, when stars fade and black holes evaporate, the laws guiding them will remain consistent. The universe will continue its quiet expansion. Particles will drift, radiation will cool, change without panic, transformation without urgency. Black holes teach us something subtle. They show that mystery does not equal danger. They show that darkness is not emptiness, but structure unseen. They show that boundaries, like the event horizon, are part of geometry, not walls of chaos. And perhaps, most gently of all, they remind us how small we are and how safe that smallness can be. Our planet is not near any event horizon. Our sun is stable. Our galaxy turns slowly and predictably. Right now, as you rest, nothing extraordinary is happening nearby in cosmic terms. The Earth rotates. The atmosphere hums quietly. Gravity holds everything in place. Black holes exist, but far away, woven into the grand architecture of reality. Let that distance comfort you. Let the vastness feel protective rather than overwhelming. The universe is large enough to contain extremes without bringing them close. Take another slow breath in and out. Feel the simplicity of this moment. You do not need to solve the information paradox. You do not need to understand quantum gravity. You do not need to calculate the curvature of space-time. It is enough to rest beneath the same gravity that shapes galaxies. It is enough to know that even the most mysterious objects in existence obey laws that are steady and consistent. And if this journey into the relaxing facts about black holes has brought you a sense of calm, a sense of wonder, or even a gentle drift towards sleep, Then before you close your eyes completely, take a quiet moment to like the video and subscribe to the channel. It truly helps this peaceful space continue to grow. You can also share in the comments where you're listening from or which corner of the universe you'd like to explore next. There are always more calm journeys waiting among the stars. Now, let your breathing slow even further. The galaxies continue turning. The black holes remain distant and serene. The universe unfolds in perfect, patient silence. And you are safe, drifting gently into rest. Beneath a cosmos that moves slowly, beautifully, and without hurry.